The study of light has been central to physics since the days of the ancient Greeks, but despite the remarkable strides in our understanding, there are still debates as to its true nature. We are going to review the way physicists understand light by looking at optics, electromagnetism, and the speed of light. The program will illustrate the way these theoretical understandings have led to the development of our use of electricity and other electronic devices. We see objects either because light is reflected off their surfaces to our eyes, or because the objects themselves are luminescent. We can see the moon, for example, because light from the sun is reflected off its surface. Amusement rides, flowers, and birds, we see all of these objects because light is reflected off their surfaces to our eyes. But a neon sign or a light bulb is luminescent. They generate their own light by electricity. In nature, we often see examples of light being reflected, as on the surface of water or polished surfaces. Mirrors offered scientists a way to study reflection, and early experiments showed that light travels in a straight line and bounces off mirrors in predictable ways. Physicists discovered that the angle at which the light ray strikes the surface, called the angle of incidence, is equal to the angle at which it bounces off, called the angle of reflection. Moving the mirror changes which rays are reflected into our field of view. By moving the mirror, we can see what is behind us without turning our heads. Changing the shape of the mirror from flat to convex causes the reflected light rays to diverge. On the other hand, a concave mirror causes the light rays to converge and intersect at a point called the focus. In both of these cases, light is obeying the laws of reflection. The light travels in a straight line, but the shape of the mirror distorts the reflected image. Another phenomenon of light is called refraction. This pencil appears broken at the waterline. The reason this happens is because light travels at different speeds in different mediums. Air is a less dense medium than water, and light waves travel faster through air than through water. When the light meets the boundary of the new medium at an angle, the light wave is bent before continuing in a straight line. This creates the distorted image. Both reflection and refraction involve a change in direction of a wave, but only refraction involves a change in medium. The refraction of light is the basis of optical devices such as eyeglasses, magnifying glasses, binoculars, and even the lenses in our own eyes. When light enters the new medium of the lens, its speed is slowed and the light ray is refracted when it enters and also when it leaves. Some lenses are convex and cause the light rays to converge. Others are concave and cause the light to diverge. The refracted light rays can be focused by the lens to form an image. In our eyes, muscles can change the shape of the lens and focus the image clearly on the optic nerve at the back of the eye. Sometimes, the shape of the lenses of our eyes doesn't focus the image clearly, and our vision is blurred. Specially shaped glasses correct this fault. By using different combinations of lenses and mirrors to form images, we can make all sorts of optical devices, from cameras to microscopes. The early telescopes were all built with lenses, but they were limited by the physical size of the lens. All of the large optical telescopes in use today are reflecting telescopes that use mirrors to focus the light. One of the most interesting devices that refracts light is a prism, an angled piece of glass. Notice how the white light is broken into the spectrum of the rainbow. 7 colors: red, orange, yellow, green, blue, indigo, and violet. Why does this happen? The reason was only discovered when scientists were able to understand the complex nature of light. What is light? It took until the middle of the 19th century before some of the basic questions were answered. In 1873, James Clerk Maxwell, a British physicist, developed equations based on the link between electric fields and magnetic fields. The oscillations, or movements back and forth of electric charges within these fields, generate electromagnetic waves of energy. Maxwell's calculations of the velocity of these waves matched the speed of light, and led him to predict that light is a form of energy that travels as an electromagnetic wave. The electromagnetic spectrum consists of bands of waves that have different frequencies, from the highest frequency waves with the highest energy to the lowest frequency with the lowest energy. The waves range from gamma rays, X-rays, ultraviolet rays, visible light, infrared rays, microwaves to radio waves. What we call light, or visible light, is only a narrow band in the electromagnetic spectrum. Included in that band are all of the colors. Each of the colors has a different wavelength. The longest wavelength is the color red, and the shortest, violet. Because of the different wavelengths, the light rays bend at a different rate when they go through the prism and create the rainbow. The tremendous energy coming from the sun is the greatest source of electromagnetic radiation in our solar system, but we can also generate light ourselves here on Earth. Fire is a source of electromagnetic energy. The chemical reaction of burning releases electromagnetic radiation that we see as light. Electric lights become luminous when electricity flows through the filament in the bulb, causing it to heat and glow when it is brought to a high enough temperature. Light travels so fast that it was once thought that it was instantaneous. But in 1673, the speed of light was first successfully measured after many observations of the orbiting moon of Jupiter. Light, it was found, took time to travel across space. In the early 1900s, while working on different aspects of the theory of relativity, Albert Einstein concluded that the speed of light was one of the fundamentals of the universe. Einstein said that matter and energy could not travel faster than the speed of light, because as matter accelerates, its mass increases, and more energy is required to accelerate it further. As it approaches the speed of light, the energy requirements become infinite. This makes it impossible for any mass to travel faster than light. After research over many years, it has been determined that the speed of light through the vacuum of space is 299,792.458 kilometers per second, or 186,282.4 miles per second. If you could travel at the speed of light, you could go from London, England, to Los Angeles, California, in less than 1/20th of a second. Imagine how far light travels in the vacuum of space in 1 year. This is called a light year and is now used as the world standard for measuring distance because it never varies. Astronomers use the measurement of the light year to calculate the vast distances between objects in space. Our solar system is in the Milky Way galaxy, which is made up of about 100 billion stars. This disk-shaped galaxy is about 100,000 light-years across, and we live about 27,000 light-years from the center. Astronomers believe there are billions of galaxies, some as far away as 10 billion light-years. When we look at the night sky, we are seeing ancient light that has taken so long to reach us, the stars that produced it may no longer exist. In the last 150 years, scientists and inventors have built on the understanding of the differing wavelengths and frequencies of the electromagnetic spectrum to develop a dizzying array of technologies that have benefited all of us. Radio waves have the lowest frequency in the electromagnetic spectrum. When a radio program is broadcast, an antenna sends out radio waves at a certain frequency, or number of waves per second. Every radio station has its own frequency. When we tune in a station, what we are doing is adjusting our radio to the same frequency of the radio wave broadcast from the station's antenna. When they are both on the same frequency, our radio receives the signal from the station and transforms it into sound waves, which we can hear. Many radio waves can be broadcast at the same time. As long as they are transmitted on different frequencies, none of them will interfere with the others. Television works in much the same way, but the frequencies are higher in the electromagnetic spectrum. An electric signal carrying information about the image arrives at the back of the television tube. Those signals send electrons to the front of the tube, creating dots of light on the screen. Those dots are quickly assembled as an image, which changes so quickly it appears to move and provide action. The curvature of the Earth limits the reception range of telecommunication signals, since electromagnetic waves usually travel in a straight line. In recent years, satellites have been placed in orbit high above Earth to get around this problem. Signals are sent from Earth to the satellite and back to Earth again. In this way, signals can be sent all over the globe. Increasingly, electromagnetic waves with higher frequencies are being used. The signals in cellular phones and telecommunication transmitters are microwaves. The same type of wave is used in microwave ovens. Radar is another use. It was developed in the Second World War to detect incoming enemy airplanes. Microwaves are sent out from a tower. The beams bounce off incoming aircraft, and some of the signal returns to the tower. Instruments read this signal to give the location of the aircraft, its speed, and direction. Today, radar is an essential tool for defense and civil aviation. Infrared rays have been adapted to help people see in the dark. Ultraviolet is used in fluorescent lighting. X-rays are used for dental and medical applications because their short wavelengths can penetrate soft tissue and show bones. The difficulty in using the waves that are higher in the spectrum is that they can be dangerous to humans. Overexposure to X-rays, for example, can lead to serious medical problems. But the more that is learned about electromagnetism, the more applications are found. By far, the most useful application of electromagnetism has been the development of electricity. The key to understanding electricity is in atoms, the basis of all matter. Atoms consist of negatively charged electrons that orbit around a nucleus made up of positively charged protons and neutral neutrons. It is the movement of the electrons that generate changes in electromagnetic fields of energy that is electric power. In 1831, Michael Faraday, a British scientist, demonstrated that electricity could be generated when a magnet was moved inside a coil of wire. Moving the magnet one way in the coil causes the electrons in the wire to flow in one direction. When the magnet moves back again, the electrons reverse and flow in the opposite direction. What is created in this process is an alternating electric current. The application of this research led to the commercial development of electricity. But how is the electricity transported? Opposite electrical charges attract, and like electrical charges repel each other. Electrons have a negative charge, and they can jump from atom to atom and molecule to molecule. When there is a buildup of electrons, they will be attracted to positively charged protons. When a negative charge has built up in one location and a positive charge in another location, and if they are connected with a good conductor, the negatively charged electrons will flow along the conductor to the positive charge. There are some materials that are good conductors of electrons, like metals, water, and the human body. Insulators are the opposite of conductors. They are materials that inhibit the flow of electrons. Examples include rubber, plastics, and glass. The copper of an electric wire is an excellent conductor. It is covered with a plastic coating, which is a good insulator. The conductor allows the electrons to flow along it, but the insulator stops the electric power from leaking out. Understanding of these basic principles led to the rapid development in the technology of electricity, which has transformed our lives. By 1873, it was shown how electric power could be transmitted through wires. And in 1879, Thomas Edison, the American inventor, developed his incandescent light bulb. By 1900, electric power is being widely used in North America and Europe, and today, electric power is used in virtually every part of the globe as the source of energy for a wide variety of uses. Most electricity used today is still generated by turning a magnet within a coil of wire. This takes a tremendous amount of mechanical energy that can be provided in a number of different ways. The water power of Niagara Falls was one of the earliest sources of power in North America. Windmills, or steam-driven turbines heated by nuclear power or fossil fuels such as coal or natural gas, can also generate electric power. Today, we use electricity to drive complicated machinery in factories, various types of vehicles, and as a source of power to run a wide range of household appliances. The benefits that we have received from the effort of physicists in unlocking the mysteries of light, electromagnetism, and electricity have been truly amazing. We see objects either because light is reflected off their surfaces to our eyes, or the objects themselves are luminescent. True or false? The angle at which rays bounce off a mirror is called the angle of. A convex mirror causes the light rays to converge. True or false? When an object is in two mediums, like air and water, its image appears broken at the boundary of the mediums. This is called. The sun, fire, and light bulbs are all sources of electromagnetic waves. True or false? Einstein said that objects can travel faster than the speed of sound. True or false? As long as radio waves are broadcast at different, they will not interfere with each other. Television is broadcast using only gamma rays. True or false? Exposure to some electromagnetic waves can lead to serious medical problems. True or false? Materials that inhibit the flow of electricity are called